A sample beam spanning 8 meters carries a dead load of 20 kN per meter, including its own weight and a live load of 24 kN at midspan. The beam is 350 mm wide and 600 mm deep, with an effective depth to tension bars of 530 mm. The beam is reinforced with 4 to 25 mm diameter bars. Assume f prime c is equal to 20.7 megapascal, if y is equal to 344.8 megapascal, if r is equal to 2.832 megapascal, and n is equal to 9. Use A sub c is equal to 21,650 megapascal and A sub is equal to 200,000 megapascal. Calculate the instantaneous deflection. Second question is calculate the long-term deflection after 5 years if 20% of the live loads are sustained. So this is the total deflection at midspan. This term here is the deflection due to this uniform load, and the other is due to the concentrated load. So to derive this equation, we have to rewrite the Venn diagram and isolate each load like this. Let us draw here the beam elastic curve so we can also draw the area moment diagram. This beam is supported at both ends. So when load is applied on top of this beam, this will deflect, and its deflected shape looks like this figure. This line is the line drawn tangent of this curve, projecting as shown. This vertical line here, starting from the curve down to this tangent line, is called the tangent of C with respect to A. And this one is the tangent of B with respect to A. So our deflection due to this uniform load is here, which is equal to CC double prime minus TC of A. So we have to know these two values to get this deflection. Now based on the figures that we have right here, we can now draw our area moment diagram so we can finally get the deflection value. If we take the moment at point B considering this uniform load W, we have W times length L times the moment arm L over 2, which is equal to W L squared over 2. So we write here W L squared over 2. Again, if we take moment at point B considering the reaction force WL over 2 here, we have WL over 2 times this moment arm L equal to WL squared over 2. So we have here WL squared over 2. Then we have here L over 3 as the centroid of a triangle. And then L over 4 for this span rail. The values here are obtained by checking moment at point C here, just like how we obtain these values here. Now let us copy this elastic curve and paste it here below this diagram. And then we draw the area moment diagram for this concentrated load. This PL over 2 is obtained again by taking moment at this point B, considering this concentrated load phi, multiplied by this moment arm L over 2. Again, this value is obtained by considering this reaction P over 2, multiplied by this lever arm L. E1 here is the area of this triangle, multiplied by this distance here from the centroid of a triangle to the point B. While E2 is the area of the spandrel, multiplied by the distance L over 4, all divided by E times I. Now, to solve for the length C double prime, we can perform proportion of similar triangles. Since we already have value of tangent of C with respect to A and tangent of B with respect to A, so by ratio and proportion, we can say CC double prime is to L over 2 is equal to tangent of B with respect to A is to L. For calculation of deflections of uncracked prismatic members, the usual formulas for elastic deflections may be used with constant value of ECIZ along the length of members. However, if member is expected to crack at any section, or if its depth varies along the span, a more rigorous calculation is necessary. Rigorous calculation includes calculating the effective moment of inertia instead of using the gross moment of inertia in this deflection equation. The code gives us this effective moment of inertia formula, which includes crack moment and crack moment of inertia. So if this is our cross-section of our concrete beam at the midspan, and we have four numbers of 25 mm diameter rebars at tension side, meaning singly reinforced beam, if we treat this as uncracked, then the moment of inertia Ig about its neutral axis is Bh cubed over 12. However, concrete is very weak in resisting tensile stresses. And any structure with concrete beam, for instance, cracks in concrete beam will be visible due to so many reasons, like prolonged vibration of its structure due to the earthquake, fatigue, creep, and shrinkage experienced by the materials as the time goes on. So during the analysis and design, cracking of concrete is considered, and if we take a look at this section, the concrete in the tension side is neglected and removed, like here. So the concrete beam flexural strength is reduced considerably. So the moment of inertia in this diagram changes, and it's called moment of inertia effective. Our cracking moment is given by ACI code section 24.2.3.5, where our FR value is given in the problem, and the YT value is this value here. Ig is the gross moment of inertia, which is already calculated here. Crack transform section diagram is all about removing concrete in this tensile region, and what left herein is only this steel reinforcement that resists tensile stress. So as I mentioned earlier, in the absence of concrete in this region, the moment of inertia of this section changes, and we are going to calculate herein what we call moment of inertia crack, ICR, which is necessary in calculating effective moment of inertia, IA. Now in this diagram, it is important to know also the new location of neutral axis before anything else. So if this is our stress diagram here, and the part where stress value is 0 is our neutral axis location, but we don't know its distance from the top of the beam. So to know the distance, let us call this distance as C. And then this distance below is 530 minus C. Let us also convert this steel area into its concrete area equivalent by multiplying the area of steel by a modular ratio which is given in the problem, and it is equal to 9. So to locate the neutral axis, we have this equation. The concrete area in this compression side multiplied by the distance from the centroid of this concrete to the neutral axis equals the area of the concrete in the tension side multiplied by this distance. Simplifying the equation, we get C value is equal to 186 millimeter. Long-term deflection is the short-term deflection plus additional time-dependent deflection resulting from creep and shrinkage of concrete. And this factor is given in ACI code section 24.2.4.1.1.